In this lesson on vector algebra, I'm going to lay down some skills so that you can resolve vectors, which includes using trigonometry to decompose those vectors and add them together and resolve them into a magnitude and direction. I'm going to remind you of some right triangle trig. SOHCAHTOA, remember SOHCAHTOA with the sine, cosine, and tangent. We're going to keep these in mind, these functions in mind when we're given a triangle, and also the Pythagorean theorem. Graphs are frequently used to represent vectors. They use a rectangular coordinate system with an xy plane, which is Euclidean space. It's very flat, Euclidean space. We're going to label the axes, and notice that the horizontal one is x and the vertical one is y. That's convention. And the scale is marked with numbers. The quadrants in the Cartesian coordinate plane are marked counterclockwise, and notice this stays consistent with how angles are measured. Angles are measured from the positive x-axis going counterclockwise. So we have 1, 2, 3, 4. We can label points in the system, for example, 3, 4. We can label that. The x is always first, and then the y. These are ordered pairs. So 3 in the x direction, 4 in the y direction, marks there. So we can keep track of that. Points that way. The origin is at the center of the coordinate system and is 0, 0, just to remind you. The difference between scalars and vectors. So we're very comfortable with scalars. Scalars are just a quantity that have magnitude but no direction. It's just a number. For example, time. Time has one direction, but we don't think about it having direction. It just is. Energy is another example. It just is, right? Dollars, they don't have a direction, right? They just exist. As opposed to a vector, which is a quantity that has a magnitude and a direction. When we think about vector quantities, we think about them pointing someplace. They point in a direction. We represent them with an arrow, a vector, in a sketch or a diagram, and with a small arrow over them. So for instance, if I have velocity, I'll put a small arrow over the velocity. Acceleration vector, a force vector, I put a small arrow over it in order to represent that that quantity is a vector quantity. So velocity and force, acceleration, we have many, many vector quantities. What we're going to note here, because we have vectors and we'll have angles because we have direction, we're going to have to assign a coordinate system, and this may be in 1D or 2D or even 3D. You may do problems. The direction is specified by a plus or minus sign to the left, right, up, or down. So for instance, I will write a coordinate system like this, where I note that to the right is a positive x and upward is a positive y. I don't draw the whole thing necessarily. I just draw two arrows designating positive x and positive y. I would, if it was 3D, I'd do a positive z. Some choices are more useful than others depending on the context. So for most problems, having a general Cartesian right positive and up positive is fine. There may be situations where you choose down as positive, and that's completely fine as well. It depends on the context as well as you staying consistent in that coordinate system. Okay, so let's think about representing vectors in a coordinate system. Draw a vector from the starting to terminal points, then determine the magnitude and direction of the vector. Okay, so in this situation, we have 0, 0 to 3, 4. So I'm going to draw those 2 points on here, 0, 0, 3, 4. This is the point I had a little bit earlier. And I can draw a vector connecting those 2 points. I'll just go like that. I'm going to call this vector R. And note that it has two sides. It has an x component, which is 3 along the horizontal, and it has a y component, which is 4 along the horizontal. When I think about finding the magnitude of this, if one side is 3 and the other side's 4, I'm going to note that this is a right triangle. And I can use the Pythagorean theorem. A squared plus b squared equals c squared. So I'm going to note that the magnitude of the vector here is going to be the square root of 3 squared plus 4 squared, which we are familiar with the 3, 4, 5 triangle. So I have 5. The length of this vector is 5. That's the magnitude. The magnitude is 5. Let's figure out the direction, and I'm going to mark in here. Here's the angle away from the positive x-axis. That's typically the way we do this. And we are given the opposite leg and the adjacent leg, which suggests tangent. I can say that the tangent of this angle, which I will call theta, tangent theta, equals the opposite over the adjacent, which is 4 over 3. When I solve for theta, I'll take the inverse tangent of 4 over 3. That'll equal theta, and you can run this through your calculator. When you do this, you get 53.13 degrees. And that's as easy as finding the vector. So we're going to take the horizontal component and the vertical component in order to find the length of that hypotenuse. And then because we have the adjacent and the opposite side, we can use tangent in order to find the angle. We can use that trig function. So let's do another example. We go from 3, negative 1, 3, negative 1, so there's that point, 3, negative 1, to negative 6, negative 6. Ooh, there's that one. Okay, so you can see that there's the vector that we're trying to solve for. And I will call this t. It's arbitrary, what we call it. And what I'm going to note is that t has a horizontal component and it has a vertical component, right? And when I look at this, 3 to 6, this side is 9 long, and this goes from negative 1 to negative 6. This is 5 long. And I'm also going to label this angle in here. I'm going to label this angle gamma. Okay, so when I think about magnitude and direction, if I want to find the magnitude of t, I can use the Pythagorean theorem just like I did on the previous one. I know the horizontal component and the vertical component. I'll go 9 squared plus 5 squared and then square root that. And when I do it, I get a little bit more than 10, 10.3. Pretty straightforward. Well, I need a direction, and what I'm going to do is say that let's find this angle with respect to the positive x-axis. This is a typical thing to do. Positive x-axis is in that direction, so we're going to find this angle, and that's the angle that we're going to, I'll call it alpha. That's the angle we're going to report from the positive x-axis. So if we find this angle theta, we're going to have to subtract it from 180 in order to get alpha. Alpha equals 180 minus gamma. So let's keep that in mind. I can find gamma. Let's see. Gamma will equal the inverse tangent of the opposite over the adjacent, which is 5 over 9, right? 5 is across, is the opposite. 9 is adjacent. And when I calculate this, you can run this through the calculator, you will get 29.1 degrees. Makes sense. It's less than 45. If they were equal, it'd be exactly 45, but it's less than. Okay, so if I wanted to find alpha, I'm going to say alpha equals 180 minus 29.1 degrees, which is a little bit less than subtracting 30. So what do I get? 150.9 degrees. And that, I will note, is from the positive x-axis. You will often want to put in there the reference. We could put this here. Also, if you've drawn this in your picture, your sketch, it's easier for whoever's evaluating your work to know, oh, here's alpha, and you calculated alpha to be 150.9 degrees. So there's an example of just vector magnitude and direction. I'm given the two components. I can find magnitude and direction. We're asked to do other things with vectors. 2D vector decomposition. So in the previous slide, we were adding two vectors together in order to get the hypotenuse. What if we know the hypotenuse? What we can do is decompose that vector. And so any 2D vector can be decomposed into two components within a designated coordinate system with an x component and a y component. And you saw that on the previous problem. There was an x component, there was a y component, and we were looking at those. The strategy here, remember, is to assign a coordinate system. We have x and y, and we need to designate positive and negative as well, especially if we're going to be adding vectors at some point. And we're going to use trig to calculate the magnitude of the components. If we know the hypotenuse and one of the non-right triangles in the right triangle, then we can calculate each side. And what do I mean by that? The first example here, a vector of length 20 is oriented at an angle of 120 degrees from the positive x-axis. Find the x and y coordinates of the end of the vector. So I'm just going to draw a coordinate system in here. And that was something that we were reminded to do, is draw a coordinate system. There's the positive x direction. I'm going to note that my vector is 20 degrees, or 20, and a length of 20 at an angle of 120 degrees from the positive x-axis, and pretend that it starts at the origin perfectly. Okay, so what I'm going to note is that this vector of length 20, what I'm going to note is this vector of length 20 ends here, which means that it's going to have an x component and it's going to have a y component, right? Y, an x and y. The x will be negative in value, right? That point, that coordinate, will have a negative value in the x and a positive in the y. So what we're going to do is note that, well, if this is 120 degrees, let's see, that means this is 60 degrees here, right? 120 plus 60 is 180. So that's a 60-degree angle. And I'm going to note y over here. I'm actually going to move the 20 into a different place. I'm going to put 20 more on top here. It's the hypotenuse. And I'm trying to find the adjacent leg and the opposite leg. Do you see how I'm going to take that 20 and decompose it into an x component and a y component? X component, y component. The x component is the adjacent leg and the y component is the opposite leg, and I know the hypotenuse. So for instance, if I say sine 60 equals the opposite over hypotenuse, so I would say y over 20, and I would get y equals 20 sine 60. So the y component in here is going to be 17.32. I can do the same with the x. X will be cosine 60 equals the adjacent over the hypotenuse, so x over 20. I do some algebra on this. I get x equals 20 cosine 60. And I get x equals 10. When you plug this into your calculator, you get you get 10. It's just this flat 10. Cosine 60 is a half of 20 is just 10. So when I look at, it says find the x and y coordinates. When I think about the coordinate, the ordered pair that comprise the end of this vector, right, this pink dot there, I'm going to have negative 10 in the x direction and 17.32 in the positive y direction. And that will be the coordinates of the end of that vector. I've decomposed it into its x coordinate and its y coordinate separately. We'll practice again here. You drive 7.5 kilometers in a straight line in a direction 15 degrees east of north. Okay, east of north. So I'm going to draw a coordinate system here, and it's going to be the standard, here's east and north, and south and west, right? It says 15 degrees east of north. Let's draw that in here. And I take this very literally. It says east of north. So I start with north and I go east of north, and that will be where my vector is, and this is the 15 degrees here. 15 degrees east of north. If it was 15 degrees north of east, I'd go north of east, right? But we have 15 degrees east of north. So this will be the vector. And when I look at this vector, it has two components. It's going to have an x component here, and it's going to have a y component here. Those two components combine in order to create this vector. Okay. If this is 15 degrees, I'm also going to note that this is 15 degrees in here, 15 degrees. When I look at the triangle, when I look at the 15-degree angle, or you could work with the 75 if you like, but I'm still working with the 15. For the 15-degree angle, x is the opposite leg and y is the adjacent leg. So watch out for this. X isn't always the adjacent. Make sure you're really investigating your problem here. And the length of this vector is 7.5 kilometers. It even gives me units. So find the distances you would have to drive straight east and then straight north to arrive at the same point. So straight east will be the x component and straight north would be the y component. So when I look at this, I have the opposite. I want to find the opposite and the adjacent, and I'm given the hypotenuse. So I'm going to have to use sine and cosine. So I'm going to say sine 15 degrees equals x over 7.5. I'm also going to say cosine 15 equals y over 7.5. Those are both true. I can solve both of these equations. 7.5 sine 15 degrees is the x. Y equals 7.5 cosine 15 degrees. And when I calculate these two, I get 1.94 kilometers. And notice that's in the east direction. And then I get 7.24 kilometers, and that's in the north direction. So I can travel 1.94 east and then 7.24 north, and that will get me to the same point. The last question here, show that you still arrive at the same point if the east and north legs are reversed in order. So it's saying if I go north first and then I go east, will I get to the same point? And the answer is yes. Right? This is still a 15-degree angle. This is still 7.5 kilometers. And it doesn't matter if I go one way or the other. Okay? And notice this results in two different triangles. They're equivalent triangles. They're similar triangles. They're exactly the same triangle. They have the same legs, the same angles, but they're drawn a little bit differently because of the order. So keep that in mind as you work on triangle problems. 2D vector resolution is when I take two or more 2D vectors to find the resultant vector. We add them together to find a resultant vector. Okay? And there's two ways to do this. The first way is graphically. And this is, to me, drawing a sketch, right? We're going to draw a sketch. And we call this the head to tail method. I'm going to take two vectors, A and B, and add them together. And what that means, I'm going to draw A, and then I'm going to extend B from the head of A. So let's say I have two different vectors. Here's A, and here's B. If I want to take A plus B, it says extend A, and then take B, extend B from the head of A. So here's the head of A, and I will put B on there. And notice that's why we call this the head to tail method. Head to tail. There's a head to the tail method right there. We don't do head to head or tail to tail. We do head to tail. Okay. If I wanted to subtract those, I'm just going to note that subtraction is the addition of a negative. I would draw A and then extend negative B. So let's draw A. There's A. And then I would draw negative B. B's in this direction. Negative B will look like this. And so I can draw negative B on here. And that would be those two vectors subtracted. A minus B is just the subtraction of a negative vector. We will determine any angle analytically. You will not be using a protractor to find angles. It doesn't make any sense to guess these angles. We will determine the value of these angles with a calculator. Don't eyeball them or guess them at all. Let's do some practice of 1D vector resolution. Just in 1D, we're still getting an idea of what's going on with vectors. For the vectors, sketch v2 minus v1, and we're just sketching them. Just sketch them. Sketch v2 minus v1. So what I'm going to do is just draw V1 and V2 to begin with. V1 is a positive 2, V1, and V2 is a positive 6, which is 3 times longer, right? Here's V2. So if I want to do V2 minus V1, I'm going to have to take V2 and add on a negative V1, and so I'm going to do this, negative V1, right? So if I take V2, which is a positive 6, and I add on a negative V1, which would be a negative 2, right? I can sketch those. And notice that I'm basically reducing the positive 6 by a negative 2, and what I'm left over is with this obviously positive 4 vector. So this is the result. V2 minus V1 is this positive 4 vector, equals a positive 4. That's the sketch. We can do this in different ways. Let's say V1 is negative 2. So there's V1. V2 is the same. It's 3 times as long, plus 6. So if I want to do V2 minus V1, so I'm going to do the negative of V1, which is a positive 2. Negative V1 is positive 2. So I'm going to take the positive 6 and subtract a negative 2, which means adding a 2. Do you all see that? And overall, when I do V2 minus V1, I'm going to get this, V2 minus V1. And you can see that it's going to be a positive 8 meters per second. This is in meters per second as well. Okay. Here I chose both negative. V2 is a negative 2, V1 is a negative 2, V2 is negative 6. I'm going to take V2 and subtract a negative V1. So there's negative V1, which is a positive 2. I'm going to take V2 minus V1. So I'm going to draw minus V1 in here, which is a positive 2. So here's negative 6 minus a V1, which is plus a negative V1. So I have negative 6 plus 2. And notice that I make up the difference in here. This would be V2 minus V1 is negative 4. Notice that's a negative 4 meters per second here. If I take negative 6 and add on 2, then that's that vector. So that's 1D vector resolution practice. You may be asked to add or subtract vectors in 1D. 2D requires a little bit more skill because we have x and y components, right? If I have 2, let's just say I have something like this, and this is 3 and this is 4, I can't just say it's 7, right? Each of these has an x component, each of these has a y component, and we're going to take these into account, and you can see that down here. Decompose each composite vector into its 2 components within a designated coordinate system. So again, we're going to assign some sort of coordinate system, and we're going to note that our first vector has an x and y component. And note that I've called these A, B, and C. So let's say that this 3 is vector A and the 4 is vector B. And so this 3A has an AX and an AY component. And also 4 has a BX and a BY component. Notice that each of those can be decomposed into each of its constituent legs. Once I get those, decompose each one into its components, the resultant's x and y components are created from the composite. So if I look at the resultant, I'm going to take, in the x direction, I'm going to take all of the little parts, all of their x components, and add them up, and it has to equal, so if I take ax and I add on bx, I should get rx in here. And I'm writing over my typing, but that's all right. This is Rx. Notice also that this is ry, right? If I go and I add ay and by, it gives me all of ry. Okay. Once I get rx and ry, notice that now I have a resultant vector that I'm able to draw in here. Notice that once I get rx and ry, I have the components of this resultant vector that's in here, right? If I take A and I add B, I get this resultant vector, the blue one. And I know that its x component is going to be ax and bx added together, and its y component, ry, is going to be ay and by added together. And that's the general strategy. Once I know the two sides, the adjacent leg and the opposite leg, I can square those and add them, and that will give me the magnitude of the resultant. And this is how we add vectors. I have an example picked out for us, and it tells us add A and B. A is 4 meters at 45 degrees, and B is 5 meters at 0 degrees. So let's designate a coordinate system. I'm just going to draw an x and y over here. X is positive to the right, and y is positive upward. Okay. I'm going to draw vector A is 4 meters at a plus 45 degrees. So I'm going to assume that's from the positive x-axis. So this is A, and this is 45 degrees here. B is 5 meters at 0 degrees, so B is a little bit longer than A. Let me make it a little bit longer than A. There's B. It's 5 at 0 degrees. I'm going to take A plus B. I'm going to draw this a little bit bigger just so I can have some space to work with. So there's A, and then there's B. Let's make B a little bit longer. There we go. Okay, so when we add these, I'm going to draw in the resultant vector here. I'm going to draw in the resultant vector here. So there's R, the resultant vector, R. Okay. And my goal will be to find Rx and Ry, given Ax and Ay and Bx and By. So here's the trick to do this. The trick to doing this is to create a nice little table. We have x components and y components. Notice that we're going to have 3 vectors. We're going to have an A vector, we're going to have a B vector. And when I add those together, it's going to be a resultant vector. So I'm going to fill in these slots, these little cells in the table here. A in the x direction, and let me go over here and draw A in the x direction. So there's Ax, and then here's Ay. And I can relate them to A and the 45-degree angle, right? A is 4. This is a 45-degree angle. Ax is the adjacent leg, and you can write this out to the side here if you like. Cosine 45 equals Ax over 4. When you do this, you can note that Ax, the x component of A, which goes in this cell right here, the x component of A is 4 cosine 45. And you can calculate this, but I go ahead and just leave it there. You can do the same thing for Ay. We're going to note that Ay is 4 sine 45 degrees. Again, you can calculate it. I'm going to note both of these are in the positive direction. There may be situations where you have negative components, and you'll want to keep track of that. When I look at B, B is only in the x direction. It has 5 in the x direction. It has nothing in the y direction. So the y component of B is 0. It's only in the x direction. So when I look at the resultant is going to be 5 plus 4 cosine 45 in the x direction, and it's going to be 4 sine 45 in the y direction. When I calculate these, when I calculate these values, this is 7.828 and this is 2.828 meters. Okay, when I write this in, right, that's this component and that's that component. 7.828, 2.828. Notice now I can calculate the magnitude of r and I can calculate the angle of r, right? We want to find a magnitude and a direction. Always magnitude and direction. The magnitude of r isn't too bad, and I'll do that over here. The magnitude of r equals rx squared plus ry squared square root. I can plug those values in. 7.828 squared plus 2.828 squared square root. And we can calculate that. The magnitude of r is 8.323 meters. Beautiful. Let's find theta. We're given the two legs of the triangle. Ry is the opposite, Rx is the adjacent. So I can say theta is the inverse tangent of the opposite over the adjacent, which is 2.828 over 7.828. When we calculate this, you will get tangent -1 of this. The inverse tangent is 19.9 degrees. So when I look at that, that'll be from the positive x-axis, which we were assuming with the other two vectors as well, right? At so many degrees, positive 19.9 degrees. So that would be the two answers from adding vectors A and B in this problem. So, to summarize, I want to see you draw these as a sketch on your paper. That is a very important skill that we will be using. This isn't just Sarah being mean and making you draw vectors for no reason. The drawings support and scaffold your problem solving, and you will see that in the previous problems that we've done, right? When I drew these out, it was a tool to help me figure out, do I need sine or cosine? Are they positive or negative? What's the final picture? What's theta? All of these visual representations help you solve the problem. So you will be drawing the head to tail method, and you will be responsible for knowing the head to tail method. And you are also required to calculate values analytically using trig functions.